In probability theory and statistics, the exponential distribution is the probability distribution that describes the time between events in a Poisson process, i.e., a process in which events occur continuously and independently at a constant average rate. It is a particular case of the gamma distribution. It is the continuous analog of the geometric distribution, and it has the key property of being memoryless. In addition to being used for the analysis of Poisson processes, it is found in various other contexts. The exponential distribution is not the same as the class of exponential families of distributions, which is a large class of probability distributions that includes the exponential distribution as one of its members, but also includes the normal distribution, binomial distribution, gamma distribution, Poisson, and many others. Characterization. Probability density function. The probability density function of an exponential distribution is alternatively. This can be defined using the right continuous Heaviside step function, h, where h equals 1. Here lambda greater than 0 is the parameter of the distribution, often called the rate parameter. The distribution is supported on the interval 0, infinity. If a random variable x has this distribution, we write x tilde exp. The exponential distribution exhibits infinite divisibility. Cumulative distribution function. The cumulative distribution function is given by alternatively. This can be defined using the Heaviside step function. Alternative parameterization. A commonly used alternative parameterization is to define the probability density function of an exponential distribution as where beta greater than 0 is mean, standard deviation, and scale parameter of the distribution, the reciprocal of the rate parameter, lambda, defined above. In this specification, beta is a survival parameter in the sense that if a random variable x is the duration of time that a given biological or mechanical system manages to survive an x tilde exp, then x equals beta. That is to say, the expected duration of survival of the system is beta units of time. The parameterization involving the rate parameter arises in the context of events arriving at a rate lambda, when the time between events has a mean of beta equals lambda minus 1. The alternative specification is sometimes more convenient than the one given above, and some authors will use it as a standard definition. This alternative specification is not used here. Unfortunately, this gives rise to a notational ambiguity. In general, the reader must check which of these two specifications is being used if an author writes x tilde exp, since either the notation in the previous or the notation in this section could be intended. An example of this notational switch reference uses lambda for beta. Properties: mean, variance, moments and median. The mean or expected value of an exponentially distributed random variable x with rate parameter lambda is given by see above. In light of the examples given above, this makes sense. If you receive phone calls at an average rate of 2 per hour, then you can expect to wait half an hour for every call. The variance of x is given by, so the standard deviation is equal to the mean. The moments of x, for n equals 1, 2, are given by. The median of x is given by, where lane refers to the natural logarithm. Thus, the absolute difference between the mean and median is, in accordance with the median-mean inequality. Memorylessness. An exponentially distributed random variable t obeys the relation. When t is interpreted as the waiting time for an event to occur relative to some initial time, this relation implies that, if t is conditioned on a failure to observe the event over some initial period of time s, the distribution of the remaining waiting time is the same as the original unconditional distribution. For example, if an event has not occurred after 30 seconds, the conditional probability that occurrence will take at least 10 more seconds is equal to the unconditional probability of observing the event more than 10 seconds relative to the initial time. The exponential distribution and the geometric distribution are the only memoryless probability distributions. The exponential distribution is consequently also necessarily the only continuous probability distribution that has a constant failure rate. Quantiles. The quantile function for exp is the quartiles are therefore: first quartile, lane, lambda, median, lane, lambda, third quartile, lane, lambda, and as a consequence the interquartile range is lane, lambda. Callback Leibler divergence. The directed callback Leibler divergence of from is given by maximum entropy distribution among all continuous probability distributions with support and mean. The exponential distribution with has the largest differential entropy. In other words, it is the maximum entropy probability distribution for a random variate which is greater than or equal to 0 and for which is fixed. Distribution of the minimum of exponential random variables. Let x1, xn be independent exponentially distributed random variables with rate parameters lambda 1, lambda n. Then is also exponentially distributed, with parameter. This can be seen by considering the complementary cumulative distribution function. The index of the variable which achieves the minimum is distributed according to the law. Note that is not exponentially distributed. Parameter estimation. Suppose random variable x is exponentially distributed with rate parameter lambda, and are n independent samples from x, with sample mean. Among the estimators of lambda, the maximum likelihood estimator is and the uniformly minimum variance unbiased estimator is. Of the estimators of the form, the one that minimizes the expected mean squared error is maximum likelihood. The likelihood function for lambda, given an independent and identically distributed sample x equals drawn from the variable, is where is the sample mean. The derivative of the likelihood function's logarithm is consequently the maximum likelihood estimate for the rate parameter is. Although this is not an unbiased estimator of, is an unbiased MLE estimator of where is the scale parameter defined in the alternative parameterization section above in the distribution mean. Confidence intervals. The 100% confidence interval for the rate parameter of an exponential distribution is given by, which is also equal to, where chi2p v is the 100 percentile of the chi-squared distribution with v degrees of freedom, n is the number of observations of inter-arrival times in the sample, and x bar is the sample average. A simple approximation to the exact interval endpoints can be derived using a normal approximation to the chi2p v distribution. This approximation gives the following values for a 95% confidence interval. This approximation may be acceptable for samples containing at least 15 to 20 elements. Bayesian inference. The conjugate prior for the exponential distribution is the gamma distribution. The following parameterization of the gamma probability density function is useful. The posterior distribution p can then be expressed in terms of the likelihood function defined above in a gamma prior. Now the posterior density p has been specified up to a missing normalizing constant. Since it has the form of a gamma PDF, this can easily be filled in, and one obtains. Here the hyperparameter alpha can be interpreted as the number of prior observations, and beta as the sum of the prior observations. The posterior mean here is generating exponential variates. A conceptually very simple method for generating exponential variates is based on inverse transform sampling. Given a random variate u drawn from the uniform distribution on the unit interval, the variate has an exponential distribution, where f-1 is the quantile function, defined by moreover, if u is uniform on, then so is 1 minus u. This means one can generate exponential variates as follows. Other methods for generating exponential variates are discussed by Knuth and Devroy. The ziggurat algorithm is a fast method for generating exponential variates. A fast method for generating a set of ready ordered exponential variates without using a sorting routine is also available. Related distributions. Exponential distribution is closed under scaling by a positive factor. If x tilde exp then kx tilde exp. If x tilde exp then x chi 22, i.e., x has a chi-squared distribution with 2 degrees of freedom. Hence, if x tilde exp and y tilde exp then min tilde exp. If she tilde exp then min x1 xn tilde exp. The Banktarder Weibull distribution reduces to a truncated exponential distribution. If x tilde exp then 1 plus x tilde Banktarder Weibull. The exponential distribution is a limit of a scaled beta distribution. If she tilde exp then the sum x1 plus xk equals tilde Erlang, which is just a gamma parametrization, or gamma parametrization, with an integer-shape parameter k. If x tilde exp then mu minus sigma log tilde gev. If x tilde exp then x tilde gamma parametrization, or gamma parametrization. If x tilde exp and y tilde exp then lambda x minus nu y tilde Laplace. If x, y tilde exp then x minus y tilde Laplace. If x tilde Laplace then x minus mu tilde exp. If x tilde exp then. If x, y tilde exp then. If x tilde exp then kx tilde Pareto. If x tilde Pareto then log tilde exp. Exponential distribution is a special case of type 3 Poisson distribution. If x tilde exp then. If x tilde Rayleigh then by 2 halves tilde exp. If x tilde exp then. If she tilde u then. If y, x tilde Poisson where x tilde exp then. If x tilde exp and then. The Hoyt distribution can be obtained from exponential distribution and arcsine distribution. If x tilde exp and y tilde Erlang then. If x tilde exp and then. If x tilde syllogistic, then log tilde exp. If x tilde exp and y equals mu minus beta log then y gumbel. Let x exp and y exp be independent. Then has probability density function. This can be used to obtain a confidence interval for other related distributions. Hyperexponential distribution, the distribution whose density is a weighted sum of exponential densities. Hypoexponential distribution, the distribution of a general sum of exponential random variables. Gaussian distribution, the sum of an exponential distribution and a normal distribution. Applications of exponential distribution. Occurrence of events. The exponential distribution occurs naturally when describing the lengths of the interarrival times in a homogeneous Poisson process. The exponential distribution may be viewed as a continuous counterpart of the geometric distribution, which describes the number of Bernoulli trials necessary for a discrete process to change state. In contrast, the exponential distribution describes the time for a continuous process to change state. In real-world scenarios, the assumption of a constant rate is rarely satisfied. For example, the rate of incoming phone calls differs according to the time of day. But if we focus on a time interval during which the rate is roughly constant, such as from 2 to 4 p.m. during workdays, the exponential distribution can be used as a good approximate model for the time until the next phone call arrives. Similar caveats apply to the following examples, which yield approximately exponentially distributed variables. The time until her radioactive particle decays, or the time between clicks of a Geiger counter, the time it takes before your next telephone call, the time until default in reduced form credit risk modeling. Exponential variables can also be used to model situations where certain events occur with a constant probability per unit length. such as the distance between mutations on a DNA strand, or between roadkills on a given road. In queuing theory, the service times of agents in a system are often modeled as exponentially distributed variables. The length of a process that can be thought of as a sequence of several independent tasks follows the Erlang distribution. Reliability theory and reliability engineering also make extensive use of the exponential distribution. Because of the memoryless property of this distribution, it is well suited to model the constant hazard rate portion of the bathtub curve used in reliability theory. It is also very convenient because it is so easy to add failure rates in a reliability model. The exponential distribution is, however, not appropriate to model the overall lifetime of organisms or technical devices, because the failure rates here are not constant. More failures occur for very young and for very old systems. In physics, if you observe a gas at a fixed temperature and pressure in a uniform gravitational field, the heights of the various molecules also follow an approximate exponential distribution, known as the barometric formula. This is a consequence of the entropy property mentioned below. In hydrology, the exponential distribution is used to analyze extreme values of such variables as monthly and annual maximum values of daily rainfall and river discharge volumes. The blue picture illustrates an example of fitting the exponential distribution to ranked annually maximum one-day rainfalls, showing also the 90% confidence belt based on the binomial distribution. The rainfall data are represented by plotting positions as part of the cumulative frequency analysis prediction. Having observed a sample of n data points from an unknown exponential distribution, a common task is to use these samples to make predictions about future data from the same source. A common predictive distribution over future samples is the so-called plug-in distribution, formed by plugging a suitable estimate for the rate parameter lambda into the exponential density function. A common choice of estimate is the one provided by the principle of maximum likelihood, and using this yields the predictive density over a future sample xn+1. Conditioned on the observed samples x equals given by the Bayesian approach provides a predictive distribution which takes into account the uncertainty of the estimated parameter, although this may depend crucially on the choice of prior. A predictive distribution free of the issues of choosing priors that arise under the subjective Bayesian approaches, which can be considered as a frequentist confidence distribution, obtained from the distribution of the pivotal quantity. A profile predictive likelihood, obtained by eliminating the parameter lambda from the joint likelihood of xn+1 and lambda by maximization. An objective Bayesian predictive posterior distribution, obtained using the non-informative Jeffreys prior 1 lambda. The conditional normalized maximum likelihood predictive distribution, from information theoretic considerations. The accuracy of a predictive distribution may be measured using the distance or divergence between the true exponential distribution with rate parameter lambda 0 and the predictive distribution based on the sample x. The Callback-Leibler divergence is a commonly used parameterization-free measure of the difference between two distributions, letting delta denote the Callback-Leibler divergence between an exponential with rate parameter lambda 0 and a predictive distribution p. It can be shown that, where the expectation is taken with respect to the exponential distribution with rate parameter lambda 0, and psi is the de gamma function, it is clear that the CNML predictive distribution is strictly superior to the maximum likelihood plug-in distribution in terms of average Callback-Leibler divergence for all sample sizes n greater than 0.